Now that we know what K is, and we know this equilibrium constant, we understand about the numerics and the mathematics of it, we can start actually calculating from experimental conditions. Now, at this point, we would have this K expression. I have a variety of different problems that we can talk about. So if I'm given a reaction and I'm given the equilibrium concentration of all the reactants and products, remember, not the initial, because at the beginning, before the reaction has started, the initial concentrations may be different. The equilibrium concentration is the ones that when it reaches equilibrium and it's no longer changing. So if I'm given equilibrium concentrations, watch for that word about equilibrium concentrations, and I'm told the reaction, I can write out the K expression for the reaction and then plug in the equilibrium concentrations into that expression and solve for it. So again, be careful. If it's talking about initially, in the initial conditions, concentrations will be different from the equilibrium concentrations. So it's going to be a different kind of more complicated problem if I'm given initial concentrations. Note that the value of K is independent of the initial concentrations. It doesn't matter what you started with. It's where it ends up, what it reaches at when it's at equilibrium. And the power of the law of mass action is that when I reach equilibrium, that magic K expression, I plug in my individual numbers, and there'll be a variety of different numbers that could get me, but I'm going to be equal to that equilibrium constant value. There is that specific ratio that when it's reached equilibrium. I can sometimes use stoichiometry to determine the equilibrium concentrations if I know the initial concentrations and at least one of an equilibrium concentration. But to do that, to use that stoichiometry, it's going to be easier to use something that we call an ice table. So we would use the changing concentrations of the material that I do know and use that to figure out the others. So let's look at what that might look like. If I'm given a reaction and all the initial concentrations, but just one equilibrium concentration, I can use the substance for which I know the equilibrium concentration of and see, well, what did it change from the initial concentration to the final concentration? The value of K, that K equilibrium constant value, is independent of the initial concentrations. But I can use stoichiometry to determine, well, if I made this much product, I know from stoichiometry I can figure out how much all of them had to have changed. And from that, I can use the change in the concentration of the material that we know both the initial and the equilibrium values for to determine the change in all the other chemicals in the reaction. So thus I can find all the equilibrium constant concentrations, and then I could use the K expression, plug them in to get the actual K value. So we're going to use an ice table, initial change equilibrium, for calculating these concentrations. So it has 3 rows: the initial I concentration, the change C concentration, and then the equilibrium concentration. We know from stoichiometry that each chemical will change by the coefficient times however many moles of reaction that have happened. And reactants are going to decrease by that negative change, and products are going to increase by a positive change if we're considering the forward reaction. So equilibrium reaction is then whatever is the initial concentration plus whatever the change is. So if I looked at this particular case, AA plus BB makes CC. I start with writing out, I make one column besides the one where I write ICE, so I'm paying attention to it. I write one column for each of the reactants and one column for each of the products. So A and B are reactants. Initially, there's some value. I'm going to call them 0 to indicate it's the initial concentration. And for the products, we would imagine at the beginning of the concentration, we're frequently going to start at 0. Unless it tells me otherwise, we will assume, oh, the reaction hasn't started, there is no products. So oftentimes, the product initial concentration is 0. Now, for the change, it's going to be related to X, however many moles react. I don't know what X is. That's the whole goal. We're going to try and find X. But I know that the reactants are going to decrease by their coefficient times whatever X, however moles react. So if it was 6 moles, it'd be A times 6. So it's subtracting AX and subtracting BX for the product. Similarly, I know how much product is going to be made, but it will be positive since it's making products. It'll be a positive, the coefficient times X. So now I can write these equilibrium expressions. At equilibrium, the initial concentration minus the coefficient times X, however many moles of reaction occurred. And the equilibrium concentration of B will be the initial concentration of B minus the coefficient B times X, however many moles of reaction occurred. And then the equilibrium concentration of C will be the initial concentration of C plus the concentration times however many moles X reacted. So if I can use any information to get one of these values, I can figure out what X is. Once I know what X is, I can figure out all of these because we know the coefficients, we know the initial concentrations. I just need one equilibrium concentration so that I can figure out what X is. And then I know what X is and I can continue on. Let me show you a specific example. Okay, oh, also, we will be using molarity in these ice tables. A little nuance that occasionally comes up. So technically, stoichiometry doesn't tell me molarity. It tells me how many moles of something reacted. If I had 6 moles of reaction occurring, then I know I'm decreasing by 6 moles times the concentration for each of the coefficients for the reactants and products. But that's in terms of moles. When we're using concentration, we're using molarity. Molarity is moles per liter. So an ice table is built around the idea of moles of substance initially and moles at equilibrium. However, if we're talking about an aqueous reaction, the volume of reaction solution is the same for all of them. So however many moles I have, I'm dividing by the same number of liters. Therefore, it turns out that they will be the moles will be proportional to molarity. And so I will, I could multiply them all by whatever that volume of solution is to convert to moles, and then from there figure it out and then go back. So for a homogeneous aqueous reaction, we can use molarity values instead of moles in the ice table, and that makes life much easier. But occasionally that comes up as a little trick. So stoichiometry is really based off moles. Molarity is moles per liter, but we will use molarity in ice tables. All right, so let's look at this one. What is the equilibrium constant for this reaction if initially the carbon monoxide concentration is 0.5 molar and the hydrogen concentration is 1 molar, and at equilibrium the carbon monoxide concentration is 0.15? Okay, again, I see I've got some initial values. I see I've got one equilibrium value. I begin by writing an ice table. So I'm going to complete the table using X as a stand-in for moles of reaction. So I put one column for each of the reactants, carbon monoxide and hydrogen, and one for the products. Note, when I'm putting these substances down, I'm not putting the coefficients in them. The coefficients are going to show up in the change step. I write down from the problem that the initial concentration of CO was 0.5 and of hydrogen was 1. And I can make an assumption, since it didn't say anything, that at the beginning of the reaction, there is no product. So for my product, CH3OH, the initial concentration is 0 molar. Now, I don't know how many moles react, but let's say it's X. Since the coefficient of CO is 1, I know this will decrease by X. For since the coefficient of hydrogen is 2, I know however many of this reacts, twice as many of hydrogen will react because of the coefficient 2. And I know for the product, since there's a coefficient of 1, it would be increasing by X. Now I can write the expression of 0.5 minus X would be my equilibrium value. 1 minus 2X would be my equilibrium value expression. And 0 plus X would be my equilibrium value expression. However, now I go back and I say, it told me that the carbon monoxide concentration at equilibrium is 0.15. So I can take this 0.5 minus X equal 0.15 and solve for X. Turns out X now, the number of moles of reaction is 0.35. Now I go back and I put in for my change. That means this is negative 0.35. This is double that, negative 0.7, and this is increasing 0.35. Now I can actually calculate the purple numbers. For hydrogen, the equilibrium value would be 1 minus 2X. So 1 minus 0.7 would be 0.3. And this would be 0 plus X. So since it didn't have any initially, it would be just 0.35. Now I have the equilibrium concentrations of all three values, 0.5, 0.15, 0.3, 0.35. At this point, I can write the K expression. I go back to this initial. It's the concentration of the products divided by the concentration of the reactants raised to their powers. So I have CH3OH divided by concentration of CO times H2. H2 is squared because it has a coefficient of 2. And now I plug in those values. And when I'm done, I get the value of 25.92. Since these were 2 sig fig, equilibrium values was in 2 sig figs, I would keep the just 2 sig figs for the equilibrium constant. So this is how we will solve for find the K constant value for a particular reaction if I'm given the initial concentrations and one of the equilibrium concentrations. If I'm just given all of the equilibrium concentrations, I'm really just have to do step 4 because I already have them. But this would be if I'm given initial concentrations.